Up next, we have computational methods for special functions. Computational methods for special functions. Well, some of these computational methods are things you probably would have seen under the under different playlists in the on this channel, like the numerical analysis playlist and all of that. So, let's see. Computational methods for special functions. The learning objectives after completing this lesson, you should be able to explain numerical stability in a special function computation. So there's something called the special function computation, which may be slightly different from what you know in normal computational mathematics that you might have come across. So then we have you apply recurrence relations for efficient evaluation. You compute special functions using numerical integration. Use arbitrary precision arithmetic when machine precision fails. Then you evaluate special functions with SciPy, manipulate special functions symbolically with SymPy. Thankfully, in fact, I got inspiration to do this playlist on special functions when I stumbled on the SciPy.special module in SciPy. SciPy is scientific Python, right? So there's this module there that is just for computing special functions. So it was from there I got the idea to just do this playlist on special functions beyond the computation. Then I should do that mathematically, like what we've been doing all along on this playlist. So then compute zeros of special functions using root finding. Okay, understand spectral approximations of special functions, and of course compute zeros of special functions using root finding methods. Then we have an introduction. Special functions are mathematical functions that appear repeatedly throughout science, engineering, and applied mathematics. And examples include gamma function, gamma of x, which we've done. We have a video on gamma, on each of them, in fact. Beta function, that's b of x, comma y. Bessel functions, j sub n of x, y sub n of x. That's Bessel function of the first kind, second kind. And then we have some other special ones. Then you have Legend polynomials, that's p sub n of x, and Hermite polynomials, h sub n of x. We have array functions, hypergeometric functions, elliptic integrals, and even things like Laguerre functions, Laguerre polynomials. So using elementary functions such as polynomials, exponentials, and logarithms, many special functions cannot be expressed in closed elementary form. The idea of special function brought to our notice is the fact that functions can be broadly classified into elementary functions and special functions. So under special functions, that's where you have all this gamma, beta, and all the rest of them hypergeometric. But under elementary functions, that's where you have what you can call polynomial functions. That's linear, quadratic, cubic, quartic, quintic, and things like that. But so apart from that, now you now have so you can basically can classify. Okay, I think I should, instead of just talking, let me demonstrate what I'm talking about. So I think I've done this before, right? That is, if you have functions generally, right, you can classify them into um, elementary functions. So functions can be elementary. So you have elementary functions, and you can have special functions. Then I said that elementary functions can then be further classified into um, polynomial, polynomial, polynomial functions, and you then have what you call transcendental functions, functions that are not uh, that are not that are not polynomials. They are transcendental functions. Of course, using things like Taylor's theorem, Maclaurin's theorem, you can actually approximate transcendental functions using you can approximate transcendental functions using polynomials. So, and then for special functions now, of course, we just only then have their types, right? So something like uh gamma, beta, all right. Um, Gamma, beta, Bessel, etc. Then coming to polynomial functions, right? Of course, you have linear functions, you have quadratic, that's order 2, you have quadratic, you have cubic, that's order 3, and so on and so forth. Then under transcendental functions, now this is where you have things like exponential functions. So here you have exponential. Okay, yeah, they are elementary, right? So you have exponential, exponential functions. You have logarithmic functions. You have trigonometric functions, right? Trigonometric functions, and so on and so forth, inverse trig, all of that. So this is a kind of overview when it comes to classifying functions, right? So this is a way of classifying functions. So um we see that these special functions appear repeatedly. So unlike elementary functions such as polynomials, exponentials, logarithms, many special functions cannot be expressed in closed elementary form. So computational methods are therefore essential for evaluating them accurately and efficiently. So first of all, let's deal with the concept of numerical stability. So an algorithm is numerically stable if rounding errors introduced during computation do not grow significantly. So that's when you say it is stable. That is, whatever happens, you don't move away too far from what the real result should be. So computers use finite precision arithmetic. For example, you have pi, which can be approximated to 3.141592653589793, and so on and so forth. It keeps going. And this cannot be stored exactly, so you have to truncate it at some point. So every arithmetic operation introduces small rounding errors. So a numerically stable algorithm prevents these errors from accumulating. So to say a system is stable, it doesn't mean that there are no errors, but the errors do not grow out of hands. That's when you say it's numeric. A, an algorithm is numerically stable. Then we have catastrophic cancellation. So consider f of x, which is equal to square root of x plus 1 minus square root of x. When x is very large, if you have a very large x, the two square roots are nearly equal because one is static, right? So they'll be almost the same. So subtracting nearly equal numbers destroys significant digits. So this phenomenon is called catastrophic cancellation. So it's more like you're subtracting, yeah, saying so you have something like 4.00000001 minus 4. That's the kind of thing we're saying here. Okay. So imagine you have x to be 10, 10 that's 10 raised power 10, right? Or e raised power 10, something like that. And then you now have square root of x plus 1 and square root of x. They are nearly the same, except that this one has 1 in addition to itself. So by the time you do that difference, you have 4.999. So that's roughly 5 times 10 raised power minus 6. That's like 0.05. So that's like 0. So what I'm saying is that 4.999996 like that is the same thing as 5 times. Okay, no. So roughly 0.12345, then like this. So, or let's say 499 something. 499. That's 12345 6. So it's pretty small. It's almost negligible, right? So that's the deal. So that's catastrophic cancellation. Subtracting nearly equal numbers, which destroys significant digits. Then we have stable reformulation. So to reformulate that, what do? So you multiply by the conjugate, multiply by conjugate to avoid catastrophic cancellation. So you multiply by conjugate, and then you now have that f of x is square root of x plus 1 minus square root of x. So the conjugate of square root of x plus 1 minus square root of x is square root of x plus 1 plus square root of x. So you multiply by up and down so that it look like you're multiplying by 1. So by the time you expand all that, so it's like you have square root of x plus 1 squared minus square root of x squared. So that'll be like x plus 1 minus x. So x cancels. So you have only one left and this one under. So you have 1 over square root of x plus 1 plus root x. So this now avoids subtracting nearly equal quantities. So this helps you to preserve that. So when you do this maths, you have, of course, you still have the same expression, but this is more or less stable. This is more or less stable, though the values are pretty close, but this is stable. Now, talking about stability in special functions, then, special functions often involve large factorials, exponentials, oscillatory terms, recursive formulas. So example, the gamma of 100 is approximately 9.33262154 times 10 raised to power 155. That's a very big number. So direct evaluation may overflow. So instead, we can then compute the log of gamma of x. In fact, even in data analysis, when you have very big data like that, you may have to take the log of of a particular variable so that you can easily visualize it, so that you will not there will not be loss of meaning in the data. So instead we can compute it and then exponentiate only when needed so that we can get the real number if that's necessary. But the log helps us to, hold it down. So see how big this number is. But by taking the log, we just have it to be, so that's the gamma of the logarithm of 100. The log gamma of 100, that's simply 359. Whereas the gamma directly is 9.33 blah blah times 10 raised to 155, big number. So we move on to talk about recursive algorithms. So many special functions satisfy recursive algorithms. Now we've seen that a lot, Bessel function, legend function, that they can be generated using some recursion kind of formulas. So many special functions satisfy recurrence relations. So a recurrence relation allows values of a function to be computed from previously known values. So if you know one or two values, you can compute the other ones, right? So this often produces efficient algorithms. So Bessel function recurrence, for instance, satisfy the fact that j sub n plus 1 of x is 2n over x, j sub n of x minus j sub n minus 1 over x. So in this case now, if you have n to be 1, so it means you need j sub 2 of x will be 2n over x, j1 of x minus j0 of x. So that means once you have j0 of x and j1 of x, once you know those two, all higher orders can be generated recursively, basically. So that's the idea of recurrence algorithms. So if we use recurrence on this now, okay, well, I mean, you can already get your J naught. So J naught, we get J naught from here, J1 from here, and then we fix them up here, and we get the estimate to be 0.352. So if I remove this, I want to see if it gives us in the original form without the evaluation. Okay, yeah, okay, it's still the same thing. It's floats 0.352. Then that's about recurrence algorithms. And then we still on recurrence, we move on to talk about forward recurrence. Forward recurrence computes F2, F3, F1, and so on, starting from F0, F1. So if given F0, F1, for instance, that Bessel thing, we can use F0, F1 to generate every other thing. Then we use it to generate F2, we use F1, F2 to generate F3, we use F2, F3 to generate F4, and so on and so forth. The advantages are that it is fast, it is simple. The disadvantage is that it can become numerically unstable for large indices. So when you keep going, it can become really big and unstable. Then we have Legendre polynomial recurrence, for instance. Legendre polynomials satisfy that n plus 1, piece of n plus 1 of x is equal to 2n plus 1 x piece of n of x minus n piece of n minus 1 of x, with p naught of x equals 1 and p1 of x equals x. So now, if we do that here, of course, you just need P naught and P1, and then you can get the rest. So we have the Legendre in this case like that. That's 0.3453862.5. Then we have backward recurrence. So backward recurrence starts at a large order and works downward. So it starts at a large order n and works downward. So one of the most important backward recurrence techniques is Miller's algorithm. It is widely used for Bessel functions, Legendre functions, Coulomb wave functions. Backward recurrence is often significantly more stable than forward recurrence. Okay. Then you have numerical integration. So many special functions are defined by integrals. For example, the gamma function is gamma of s equals integral from 0 to infinity x raised by s minus 1 raised to minus x dx. So numerical integration allows us to evaluate such functions. So since we're not able to express them in closed form, like in terms of polynomials or some other transcendental functions, then you can actually get numerical approximation. And that is where rules like trapezoidal rule comes in. So the trapezoidal approximation is integral from a to b of f of x dx, which is approximately h, which is the step length, into f of a plus f of b all over 2 plus summation from I equals 1 to n minus 1 of f of x, comma f of x of I, where h is b minus a over n, like that. I dealt with all of this under the numerical analysis playlist, which you want to check. So this is us defining the trapezoidal function here. Now we need a function, we need the limits, the integral limits a and b, and then we have n plus 1 here. Then y is the f of x, the function. H is b minus a over n. Then you return this expression now, h into 0.5y plus 0.5y minus 1 plus np all of that. So describing whatever expression we might have. So in this case, now if you want to approximate gamma 5, so we know gamma 5 is 24 normally, but if you evaluate gamma 5 as integral from 0 to infinity of x raised to 4 e raised to minus x dx, you know, so this is the approximate result. So because if we try to solve this, it's all right. We know this is 24, right? But when we do the numerical, we get 23.99, which is pretty close to 24, by the way. Then we have Simpson's rule, which is another numerical integral method. So Simpson's rule, I think I dealt with all this one after the other under numerical analysis. I took them one after the other to explain how they work and took several examples, some examples, right? So for Simpson's rule, now we have integral from a to b, f of x dx in approximately h over 3 into f naught plus 4f1 plus 2f2 plus 4f3 plus all of that all the way to fn. So the error behaves like big O of h4, okay? And then we have adaptive quadrature. So SciPy provides adaptive integration through quad. So adaptive methods automatically refine regions where the integrand changes rapidly. So here now, from SciPy.integrate, we can import quad. So that's for quadrature. So import number as NP. So if you define a function like x raised power 4 e raised power minus x, just like what gamma of 5 is. So you see that this quadrature thing works even perfectly. So you now have, so you get the value and the error. So quad, the function f from 0 to infinity, you get exact value of 24, like what you would have got if you did gamma of 5, which is 4 factorial, right? So adaptive quadrature seems to be that uh, accurate. Then we have Gaussian quadrature. So Gaussian quadrature approximates integral of -1 to 1 of f of x dx using summation from I equals 1 to n, w sub I, f of x sub I. By the way, for continuous variables, right, integral is used for summation, but for discrete variables we use this summation to sum. So it's integral and summation are technically the same, except that one works for discrete numbers, that is numbers that you can count separately, while continuous integral works for continuous functions which you cannot count apart, maybe when you're dealing with decimals and things like that. So here now where nodes xi and with wi are optimally chosen, and it often achieves very high accuracy with relatively few points. So if we try that here, so for SciPy to SciPy integrate, we import fixed underscore quad. So import number as NP. So and then you define this function that's exponent of x. So you get the value and all that. So if you print this value now, you have 2.35, blah blah. Then we have arbitrary precision methods. So standard double precision arithmetic provides roughly 15 to 16 decimal digits. So some scientific computations require hundreds or thousands of digits. So examples, you have number theory, quantum mechanics, zeta function computations, like that. Then using MP math. So the MP math library provides arbitrary precision arithmetic. So look at this. So from MP math, you import MP. So MP.dps is now 100. So like this is like 100 decimal places for pi. So that's 3.141592 and so on and so forth. So it just keeps going like that. So if I want it to be 1000, of course, that's going to be long, very long, way longer than this. So it just keeps going like that. So that's the deal here. So if you want things like that, you can work with it. All right. So then we have high precision. Okay, I want to try this for oh, okay. Wow, this thing can read my mind. So mp dot e mp.e. Okay, so I run that. So you see that's 2.718 blah 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 like that. So this is pi, this is exponent, that's e. Then we have high precision gamma function, right? So for this, maybe you want 80 decimal places, you want gamma function to 80 decimal places. So you have this. So this doesn't yet have any decimal, so like that. Then we have high precision Bessel function. So for Bessel function, you also get that, right? 10, 5, you get that high precision Bessel function. Then next we talk about SciPy special functions. Yeah, like I said, I got the idea, I got the inspiration to do a playlist on special functions when I did when I completed the playlist, I started like 2 years ago on scientific computing. So under SciPy, I came across special functions. So that was where I got the inspiration to teach to do this playlist I'm currently doing. So SciPy special functions now. So the module for special functions in SciPy is SciPy the special. So and it contains efficient algorithms for many special functions like gamma functions. So gamma n is n minus 1 factorial for positive integers, that is. So if you now do gamma 5, so you have import SciPy the special as SP, then from SciPy special import gamma, right? So you run, you get to 24. For beta function, you also have that. Beta b of a comma b is gamma a gamma b all over gamma a plus b. So from SciPy the special, you import beta, and then you print beta 2 comma 3, and you get your result like that. That's like 1 over 12, I think, the last time we did that. Then for error function, you have error function of x equals 2 over square root of pi, integral from 0 to x raised for minus t squared dt. So from SciPy, especially import ERF. So you print ERF at 1, and you get 0.842700 9007929497148 like that. Then you have Bessel functions. So you have all the special functions. I mean, we've been through all of this. So this is just to show, it's more like a recap, right? So we have all these things. So legend functions. So of course you can switch values to see if you need to see other things, right? Then you have array functions, which is a combination of growing and growing. So one part is growing, the other part is decaying, that kind of thing, you know. So we have that. This is the array function. These are array functions now. Then you have zeros of Bessel functions. So, you have the zeros now. You have the first four, first five, 1, 2, 3, 4, 5. That's 0, 1, 2, 3, 4, like that. Then now we have the SymPy method. SymPy is symbolic. So if you want to have the exact way instead of numerical way, SymPy does it. So if you want numerical, SciPy does that. SymPy does the exact form. So SymPy provides symbolic computation capabilities. Unlike SciPy, SymPy manipulates exact mathematical expressions. So you have symbolic gamma function, for instance. So instead of giving you a numerical thing, so you just get your gamma just the way you would have it, given in terms of gamma. Now, sometimes you may want to print. So if I print this now, it won't be this pretty, it will just be, you just get something not as pretty as this. Okay, so it just takes, say, gamma x, but if you want to have the symbol, you just don't use the print. Then you have series expansion of Bessel function. So for series expansion of Bessel function, so if you also print this, you won't get something this pretty. You just get it scatter like in something in LaTeX, right? So you have Bessel J 0 comma x series x 0 to 8. So if you want to keep going, say you want to go, let me try 80, just something out of the, yeah, so you see that's a lot. That's a whole lot. And that was fast, by the way. So that 80 is too much. So let me do 16. So that means I'm going to get up to x raised to power 14. So that still fits on one screen like this. So yeah, so that's Bessel J. So and that's the power of SymPy there. So from SymPy you import Bessel like that. So the expansion, okay, yeah, what we started with was this 8, right? So let me just leave it that way so that we have power up to, yeah, so it just continues after x raised to 4 over 64 like that. So, and then we have symbolic differentiation. So you have from SymPy import gamma different symbols. So you want to differentiate gamma of x. So that's gamma x polygamma 0 comma x. That's what that gives, Then you have high precision evaluation. We've seen things like that before. So from SymPy import gamma, so you have gamma 3.5, evaluate up to 50 decimal places. What if I want just 30? So it's shorter than this. So it all depends on what you want. If I want 300, it's way longer than, 300? Are you telling me this is 300? Interesting. Okay, so that's what that looks like. Then we have spectral methods. Spectral methods. I think I talked about spectral methods still under numerical analysis, especially on the border between numerical analysis and partial differential equations. So spectral methods approximate functions using global basis functions. Instead of f of x equals a naught plus a1x plus a2x squared and so on, we use f of x to be summation from n equals 0 to infinity a sub n phi sub n of x, where phi sub n of x are basis functions. And then we have some common bases like the Fourier basis, Chebyshev polynomials, Legend polynomials for smooth functions. Spectral methods often exhibit exponential convergence. So I think I did something like this under the numerical analysis playlist, which you want to check if you need to do something with numerical analysis. So a periodic function can be represented as f of x equals summation from k equals minus infinity to infinity c sub k e raised by I kx. All right, that's Fourier spectral expansion as demonstrated here. Okay, so we have n to be 64, and then we have from 0 to 2 pi, and f is actually sine 3x. So this is also evaluating sine 3x using some Fourier stuff, and we get all of this. So we have Chebyshev approximation. So Chebyshev polynomials are, I think we did this also in a previous video. So Chebyshev polynomials are t sub n of x equals cos n arc cos x. So they are widely used in numerical libraries because of their excellent approximation properties. So we have Chebyshev coming here like that. Then we have zero finding methods, right? Many applications require zeros of special functions. So it's more like you're solving a function. Say you just want to solve sine all the values of x that satisfy something like sine x equals 0 or sine x plus cos x equals 0 or whatever else you may be interested in. So many applications require zeros of special functions. Examples, you have j naught of x equals 0, p n of x equals 0. So these zeros are important in quantum mechanics, vibrations, waveguides, and spectral methods. So to find zeros of functions like that, you need things like bisection method, which I dealt with under numerical analysis. So you have bisection method, and the idea of bisection method is that it is clear that if you have a function f of x, right, the solution to f of x, okay, if you have f of x equals 0, right, you have and and x lies between a and b, that x is in between a and b. By all means, the function evaluated at a multiplied by the function evaluated at b must be less than 0 for this to be true. So, if that is true, so that means that this solution you're looking for, the first iteration you have to do, you have a, b. So your x, you can say x1, it lies between a and b. If that is the case, this has to be plus and this is negative, or this has to be negative and this is positive. Oh, okay, no. Let's assume that after evaluating, right? If you evaluate the function at a, you get minus. Evaluate the function at x1, you get minus. You evaluate the function at b, uh you get plus. So automatically the function cannot be found between a and x1 because they are both negative. So the signs have to be different. So it means your solution can only be found between x1 and b. So your second iteration will have to now be like this. You have x1, you have b. This is already negative. This is positive. Then we have x2. So by the time you look for x2 and x2 is now positive, so it automatically means that your solution cannot be here because your solution only lies within a place where the signs are different. So it means, so this is the bisection method. So you keep cutting off parts where the solution cannot be found. And by doing that, you keep narrowing it down. So the next iteration is going to be something like this. You have x1, you have x2. From up here, we know x1 is negative, f of x1 is negative, and f of x2 is positive, and then you're looking for x3. So now let's say x3 is now negative. You cut this off again, and then your next solution lies between x3 and x2. So that's how you keep going for bisection. So you're cutting off regions where the solution does not exist, so you can improve your chances of getting the solution. So suppose f of a multiplied by f of b is less than 0, then a root automatically lies between a and b. Repeatedly bisect the interval until the root is isolated. So that's what I just demonstrated up there. And this Python code to deal with something like that. So you define a function bisection. You need a function f, the limits a and b. And of course, you need to set a tolerance. That will tell you how fast your solution converges, depending on your tolerance. The level of error you can tolerate. That's what that's it for. So while the absolute value of b minus a is greater than the tolerance, then c has got to be a plus b over 2. If f of a multiplied by f of c is less than 0, then b is equal to c. Else a is equal to c, and you return to a plus b over 2. So you keep doing that. So I run this now. So imagine you want to compute square root of 2. So to compute square root of 2, right, it means, to compute square root of 2, to compute square root of 2, So you can let x be square root of 2. So if you let x be square root of 2, that's square both sides. That's x squared equals 2. As a function, you then have x squared minus 2 equals 0. So it means if you can solve for x, you'll be able to compute the square root of 2, right? So here now, so compute square root of 2, you have x squared minus 2 equals 0. So you can set this situation up for it. So f now, you're still referring to this bisection formula, by the way, don't forget. So you now quickly define a function. Lambda x is x squared minus 2. That's x times x minus 2. So the root is bisection. So you are now calling this bisection formula. So the function now is this lambda function that you just defined, right? And then the limit is 1 and 2. You are looking for the solution between 1 and 2. So if you print the roots, you discover it's 1.4142, blah, blah, which is pretty close to the actual square root. Okay, let me even show that. It's actually close to the actual square root, SQRT, of 2. I know this may not work. I may need to do some other things. I get it. So uh, what's that thing called now? Um, I have to mount it by import. Yeah, I import, sorry. So import math. So it's only from math that I can't get square root. So math to square root now, then I can go. So you see that's 1.41421356. So you see a bit of difference. So they stop looking alike after at 2, 3. So everything goes differently. Okay. So if I increase the tolerance limit, for instance, maybe I can get something more accurate. Then we have Newton's method, which is known as one of the fastest converging methods. So some people call it Newton-Raphson's method or Newton's method, so whatever. So it's one of the fastest in finding zeros. So Newton's iteration is x sub n plus 1 equals xn minus f of xn over f prime of xn. It converges quadratically near a root. So that because of quadratic convergence, it's really fast. So imagine, so we can define Newton f df x naught. That's changing f. So x is equal to x naught. So for everything in range n now, you have x equals x minus fx over dfx. So if you return that now, f is now lambda x squared minus x, df is now 2x. So derivative, so this only works for some functions that are differentiable, right? So, and if you do the Newton thing here, so you also get 1.41213563. So this even looks a bit more accurate than this because here you have 235, here you have 237. So Newton-Raphson converges faster, that is, for the same tolerance. It gets closer to the answer compared to the bisection we considered the other time. Then you have the second method. So the second iteration is x sub n plus 1 equals xn minus f of xn multiplied by xn minus xn minus 1 all over f of xn minus f of xn minus 1. Unlike Newton's method, derivatives are not required here. So it's more like you're just doing some geometrical stuff here for second. Then finding Bessel function zeros. So the first positive zero of j naught of x occurs near x is approximately 2.40482555 like that. So and if you run the code, we have SciPy special import JV, that's Bessel there of the first kind. Then in SciPy optimize import root scalar. So if you do all that, you get something as close as possible to this. So it's close up to 5557, before it begins to deviate. Then you have the Brent method, which I only came across preparing for this video. Every other method I think I've known, but Brent's method, this is my first time of encountering it while preparing for this, right? So Brent's method combines bisection, secant, inverse quadratic interpolation, and the advantages are that you have guaranteed convergence. You have high speed, and it's widely used in scientific software. So you have this now for the same Bessel approximate zero there. You have 2.4040482557. So it also gets to 5557 like this other one. And then it starts deviating too. So in summary, in short, we're saying that computational methods for special functions rely on several key ideas. First of all, numerical stability prevents loss of accuracy. Recurrence relations provide efficient evaluation. Numerical integration computes integral defined functions. Arbitrary precision overcomes floating point limitations. SciPy provides fast numerical implementations. SymPy provides symbolic manipulation and exact formulas. Then spectral methods provide highly accurate approximations. Then root finding algorithms compute important zeros and eigenvalues, right? So together, these methods form the foundation of modern scientific computing involving special functions. So then we have our practice problems as usual. So here you can see questions 1 to 5 on the screen, questions 1 to 5. Of course, I'll be solving 2 of them as usual. So questions 1 to 5. So I'll be solving question 4. Implement Miller's backward recurrence algorithm for Bessel functions and compare its accuracy with forward recurrence for others n equals 20 through n equals 50. So we'll be trying that out and we'll see how that goes. Okay. So apart from question 4, the other one will be 20, which I'm going to show you when we get there. So you have 1 to 5 here. You have 6 to 10. Question 6 to 10 here. Question 6 to 10. Then you have 11 to 16, or 11 to 15, right? 11 to 15. And finally, 16 to 20. So I'll be solving question 20 also. Consider the transcendental equation gamma x equals 10. Use a numerical root finding method to determine all real solutions and verify them numerically. So let's go for that, shall we? Problem 4 for starters. Okay, so now problem 4. Problem 4 says to implement Miller's backward recurrence. Miller's backward recurrence algorithm for Bessel functions. And compare its accuracy with forward recurrence for orders n equals 20 through n equals 50. So in step 1 now, step 1, we do the Bessel recurrence relation. Bessel recurrence relation, that's the first thing. So we know that Bessel function satisfies it satisfies that j sub n plus 1 of x is equal to 2n over x, j sub n of x minus j sub n minus 1 of x. Bessel function satisfies that. So this relation can be used either forward, we have the Milner backward and the other and forward. Forward from lower orders to higher orders. It can also be used backward. It can be used backward from higher orders to lower orders. Okay. So from lower to higher orders, that can be done. Now, we look at the Milner part, which is backward, and then we compare with another one, which is forward. So then we have, so having done that, we go for step 2. In step 2, we are talking about why forward recurrence may fail. Why forward recurrence may fail. Okay, so suppose suppose x is equal to 1, and we wish to compute j sub 50 of 1. Okay, since j sub n of 1 is approximately 1 over n factorial, 1 over 2 raised to power n, 1 over 2 raised to power n for large n, the values become extremely small. For example, well, let me change markers here. So for example, J50 of 1 is approximately 2.9 times 10 raised to power minus 80. That's as good as 0, right? That's pretty small. So in forward recurrence, each step introduces small rounding errors. So the recurrence contains the recurrence contains the amplification factor 2n over x, right? We have that. So then we know that at n equals 50, and x equals 1, 2n over x will be 2 times 50 over 1, which is simply 100. We have that. Thus, small errors are multiplied repeatedly. Small errors are multiplied repeatedly, eventually dominating the true solution. So consequently, forward recurrence becomes numerically unstable for large orders. Okay, so we go for step 3, right? Step 3, where we talk about Miller's backward recurrence. Miller's backward recurrence. For Miller's backward recurrence, right? If we choose a large order, say n is far greater than 50. For example, n is equal to 100. So then we can then assign arbitrary starting values. Say J101 is equal to 0, and J100 is equal to 1. So in that case, if we apply the recurrence backward, applying the recurrence backward, we have Jn minus 1 equals 2n over x Jn minus Jn plus 1. So, that's a reversal of what we should normally have, right? Let me see. Where's that? The first express. Yeah. So now, so it means that we are getting Jn minus 1 coming here, and this one comes over here. So we are going backwards like this. So with that, now we have Jn minus 1 equals 2n over x. So you see 2n over x has even come over. Oh yeah, 2n over x has always been like that. Jn minus Jn plus 1. So with that in place, this generates J99, J98, all the way down to J0. And the resulting sequence has the correct relative proportions, but not the correct scale. That, and then we move on to step 4. So in step 4 now, we can talk about normalization. So the identity J naught of x plus 2 summation k equals 1 to infinity of J sub 2k of x is equal to 1 can be used to determine the normalization coefficient. So after scaling, all computed values become accurate approximations of the true Bessel functions. Yeah, so that takes us to step 5, which is the last step for this problem, by the way. So step 5. So in step 5 now, we can talk about the comparison. So for orders between 20 less than or equal to n less than or equal to 50, forward recurrence gradually loses accuracy because round of errors grow at every step. Then backward recurrence suppresses the unwanted growing solution and converges toward the desired Bessel solution. I mean, so what we are simply, so in essence, we can see that forward recurrence is efficient for small orders, right? I think I should write that. Therefore, first, forward recurrence is efficient for small orders, first of all. Secondly, Miller's backward recurrence is the preferred method, for large orders. Then modern scientific libraries frequently use backward recurrence internally. So Miller's algorithm is one of the most important numerical techniques for special functions because it converts an unstable forward recurrence into a stable backward computation. So for large order Bessel functions such as J50 of I, backward recurrence produces highly accurate results, while the forward recurrence may become completely unreliable. So let's quickly go for number 20. That's problem 20. So for problem 20 now, so consider the transcendental equation gamma of x equals 10. So we need to use a numerical root finding method to determine all real solutions and verify them numerically. Okay, let's move on with that now. So first we need to define the equation, right? So we seek real solutions of gamma x equals 10. So equivalently, gamma x equals 10 can then be written as f of x equals gamma x minus 10 equals 0. That's what we are looking for. So since the gamma function is continuous between the poles, roots can be located by studying the graph, right? So that's one thing. Another thing, so important properties of the gamma function. So we need to recall. So recall that gamma 1 is 1, gamma 2 is 1, gamma 3 is 2, and gamma 4 is 6, gamma 5 is 24, and so on and so forth, right? So we can say therefore, so since this is what we have, right, that gamma minus 10, gamma x minus 10 is equal to 0. So that means we need some value of x that is very close to 10. So in this case now, we know that 6 is less than 10 and 10 is less than 24. That means we know 10 lies between 6 and 24. So the other, as we do this, we keep looking for values. If we can get, if we're able to get 10, that would have done the job. But now we know gamma 4 is 6, gamma 5 is 24. So it means that this 10 we are looking for lies between 6 and 24. So since gamma x is continuous, since it's continuous on the open interval 4, 5, right? So you see, this is 4 and this is 5. So the special ones, 4, 5. So it means that one root must lie in this interval, So it means the answer we are looking for is somewhere between 4 and 5, basically. So then we go on to talk about first to find the first positive solution. So using interpolation, right? Using interpolation, we know that gamma 4 is 6. And then we know that gamma 4.5 is approximately 11.6317. Okay, that's gamma 4.5. So, and since we know that 6 is less than 10, it's less than 11.6317. All right. So that means the 10 that should have answered that perfectly lies between 6 and 11.6317. So the root lies between, so it looks like some kind of bisection, 4 less than x less than 4.5, like that. So a numerical root finding procedure gives x1 approximately 4.390843, right? As a numerical root finding procedure, it's given that. So so for verification, right? So for verification, we see that gamma of 4.390843 is approximately 10. This, so next thing is to search for additional positive values in step 4 now. Okay, I've done my writing steps. So we want to search for additional positive values. So we know that the gamma function decreases, it decreases from gamma 1 equals 1 to a minimum near x, which is approximately 1.4616. So where gamma x is now approximately 0.8856. Then it increases monotonically for x greater than 1.4616, because just like what we saw up there, because 10 is greater than 0.8856, there must be another solution between 1 and 0, right? Between 1 and 0. So checking values, we have that gamma 0.1 is approximately 9.5135. Then gamma 0.09 is approximately 10.57. Okay, so that means that thus a root exists between 0.09 less than x less than 0.10. So numerical solution gives x2, which is approximately 0.096823. So to verify that, right? Verification again, verification. If you check gamma 0.096823, that's approximately 10. Okay, so that's another solution right there. Now, another question we want to ask is, are there any negative solutions? Do we have negative solutions? So, are there negative solutions? We've got like two solutions. Are there negative solutions? So the gamma function has poles at x equals 0, -1, -2, -3, and so on, and oscillates between these poles, between these poles. So on each interval, that's -n to -n+1, the function passes through all real values from -infinity to +infinity. So since 10 is a positive number, there is exactly one solution in each interval, that is -1, 0 and -2, -1, like this. There's exactly one solution in interval -1, 0, -2, -1, then -3, -2, and so on. So therefore, infinitely many negative real solutions exist. The first few are approximately x, which is -0.7408, another x -1.8480, another x -2.9128, and so on and so forth. Finally, we can say that the equation gamma x equals 10 has two positive real solutions. That is, x is approximately 0.09 6823. Then we have x is approximately 4.390843. Those. Then that's so it has two positive real solutions. Very important. Two positive real solutions. And that's not all, right? Another one. So we have two positive real solutions. We also have infinitely many negative real solutions. One in every interval. Minus n to minus n plus 1 for n equals 1, 2, 3, and so on and so forth. Because of the poles of the gamma function. So in the final remark here is that this problem illustrates how numerical root finding combines with analytical properties of special functions to locate all solutions of a transcendental equation. All right, so that's how that has been. It's been a lengthy one, but thankfully we are at the end of that. So I'll just flash the questions once again and end this. So see the questions once again. So here you can see up to problem 5, then 6 to 10 here, 11 to 15 here, then 16 to 20 here. Let me know how helpful this is for you. And if there's something else you've been tried out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you have not, good time for you to subscribe. Go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join. That gives you some special privileges that you find out when you click on join. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.